So, as you might have noticed, I'm not Lucas. He couldn't come today, so I'm replacing him. So we're gonna do something a little bit different than we are doing previously. We're gonna have it's something more related to the first part of the course. So let's consider this just a small stop in the course and some appendices of some sort. So let's just said this has more to do with the first part of the course. So let's remind you of some definitions. Basically, I'm gonna need to go back to the generality of that correlations inequalities, FKG and GKS inequalities. So let's go a little bit back to that. So let's start. Let's say recalling the first part of the course. So in the first part of the course, we had, first of all, we're considering interactions, general interactions, so X and Y on the lattice, no negative, okay, so only ferromagnetic systems, no negative. For short, we are just gonna call this thing here, this family, J. So J will be the family. And we had external fields also, again, a family of this sort, on ZT, again. And for now, let's assume real, okay? We're gonna need to make a little bit change of that, but in the future. And again, the configuration space is gonna be -1 and 1, again on Ising models, Ising type models, and when I put some subset here, I mean -1 and 1, lambda finite, lambda subset of ZT. Okay. Let me see if I need something else. Yeah. For now, in this generality, we had maybe here too small. So let's try it. We had the Hamiltonians, right? The energies in the box with this interaction and this external field of a configuration, something like this: J, X, and Y, sigma X, sigma Y, Y and X and Y in the box, minus, right? And you have a one body perturbation, X in the box. And you had states, right? So for F local, for a local function, you had the states again, lambda. Here I should put the interaction, but it's gonna be fixed. It's gonna be always this J, so I'm gonna just omit it. I'm gonna just put the external field, and this is, as you recall, you sum overall configurations inside the box, and you put exponential of the Hamiltonian. There's a beta here, the temperature, which I'm also not gonna keep writing down because it will always be fixed, and a partition function. Again, I will omit J. So in this generality, Lucas announced the FKG inequality or GKS inequality and so on and so forth. But you remember, maybe I think even last class, you have a boundary condition on this stage, right? Yeah, there's nothing of this sort here, but you can recuperate the boundary condition. So if you take a eta here, any configuration, if you take this external field, H eta, it's gonna be, so you just copy the external field and you add something like this. You sum on J, X and Y, eta, y, and you sum over all y times not x, and is outside of the box. Again, x on zd. So if you consider this external field, then you recuperate what we're doing before. So if you take a local function on lambda with this external field, then again this is the state or the measure with eta, and hopefully this is the notation Lucas is using. If it's not, this is what you expect. So it's the sum over local configurations. Here you have function, you have the Hamiltonian, and here is again sum of the interaction x, y, sigma x, sigma y. Here is inside the box, both are inside the box, and you have there's always a beta, right? A beta here, a beta here. Have the external field on the box, and you have the so-called the boundary condition here. So j, x, and y, sigma x, eta y. Again, let's say x in the box, y outside the box. Right. And there is a partition function. A partition function, you've seen this a lot, so I'm not gonna write it. And you get this back. This is gonna be this transformation is gonna be very useful later on. And I think yeah, that's all. Let me just recall one last theorem we saw the next time. That's actually the goal, and I'm gonna present this theorem, and then I'm gonna tell you the goal of this class. So the theorem that you saw before is that you take j the interaction jx and y, x and y on z and t, translation invariant. Then what happens is that these extremal states with h here maybe let's put no external field, so I'm just going to put here 0. If there's no external field, you can consider constant external field also, but let's say it's 0. And so if this happens, if for all, again, these are the infinite states, so this happens for all local functions. So the states are equal for all local functions if and only if the mean at 0 is the same for all functions, right? But if you go back to the proof and redo it a little bit, you see that you proved something actually a little bit different than that. What we actually proved was this. This happens again if and only if the mean is the same x minus for all x on zd. Okay, you actually proved that this happens if and only if this happens. But because the system is translation invariant, then both the second and the third equations are equivalent. And the goal of this class is to prove a theorem that's a little bit stronger than this, but it's more restrictive. That our goal is to, yes, I have a good color, change this for some x, only that. So means that if the magnetization meets at on one side, then the states must be the same. We are not gonna be able to use. We're gonna need some restriction here. We are gonna also introduce an external field here. We're gonna keep an external field, but now we're gonna consider external fields that are not constant. They will not be real. They need to have the same sign, so we're gonna assume positive. So we're gonna replace the zero here, or this constant external field, for any external field with another condition. This is the goal of our class. And to do so, I'm gonna use another correlation inequality, set of correlation inequality, that's called duplicated variables inequalities. Okay, so let's start with the duplicated variable. Okay, maybe this is fine. So we need to duplicate variables inequalities. For short, DVI, right? And these inequalities consist of you do a small trick of duplicating the state space. So now the state space it's not gonna be just sigma or sigma lambda. The state space now is so the state space is now the product. You've seen this actually in the proof. I think maybe GKS inequality, but it may be on FKG, I don't know. But we've seen this trick before, but I'm going to give more details now on what you actually do. So here you have this duplicated state space, and you have two families of external fields. So you have our usual family, and you have another one. I'm going to call H prime, right? So H prime is just a family H prime of X in ZD. As I said, the interaction is gonna always be that family J with P. So the Hamiltonian of this duplicated system, I have H and H prime, and I have two configurations, sigma and sigma prime. This is just be the sum of the Hamiltonians. Okay. Very simple. Lambda and H prime of sigma prime, right? And again, I can define the state so the duplicated state, so the duplicated state gonna be something like this, state F. Now the state space is different, so maybe let me write this. But the definition of local still holds, so it's the same definition of local you saw, local. And the state space of F. Here, I'm gonna write down both external fields. It's just, again, you take sigma and sigma prime here. f sigma sigma prime, and the exponential of minus beta sum of the Hamiltonians. Maybe let me erase this part here. Here you have the sum of Hamiltonians, right? H sigma and H prime. And again, you divide by both partition functions. So and H. You can write this, or you can write a partition function of the duplicate state. It's the same thing. And for these states, again, let me show some important definitions. Okay, first of all, we know that the local function we all actually care about, because you saw that local functions are always polynomials, right? The local function we want to study, for example, sigma of an x, right? This is defined like this. Sigma x, and this is the product of x in x, omega x. So this is one example of local function we had before, right? The state space is now changed, so this is not a local function anymore of this form, but there is a clear extension, right? You can extend this. You can extend this to our space. You just do something like this. So you have omega and you have omega prime, right? And it's the same definition. You just ignore the second variable, omega x. Let me say x here is a subset of the D, right? Oh, the bond. So you just ignore the second coordinate, and you have this local function. And analogously, another very important local function is we're going to call sigma prime of x. That is defined like this. So you see, we are in the duplicated space. So another local function is this one, and now you do the same, but now you ignore the first coordinate. And x, omega prime x. Yes, so this is an example of local function. This is an example of local function. Let me give two more examples of good local functions that are very important. Another examples of local function will be these. Again, take an x on the D, and you take big X on a subset, and you define S of, yeah, maybe my S must be there. So S of X, this is just gonna be the sum. You sum these two on X. You see? Sigma X prime. And you have this Tx, it's gonna be sigma X minus sigma X prime. So you see, this is one is summing and one is the difference of this being in each state. And just like we did here, S of a subset is just the product of S, X of X, and T of a subset is just the product of x in x, Tx. Yes, and these, notice that these functions, they have a very useful property that they satisfy this. It's easy to see that if x, mm, let me, okay, let me start with this one. Easy. If x, s of x is 2, is actually plus or minus 2. If this x of x is plus or minus 2, then t of x is equal to 0. Right? Because in this case, they spins coincide, and that one's the difference. And the converse, sort of converse, also holds. So if tx is either plus or minus 2, then s of x is actually 0. Again, because in this case, the spins do not match, so this thing is going to be 0. This is actually pretty useful. It's going to be very useful to us. And okay, let me remind you of another thing, just to ease up a little bit the notation. Again, that this state space we defined has no boundary conditions, right? So sometimes we wanna deal with systems with boundary conditions. So, but you can maybe you can check, but it's quite easy to see. We're gonna denote this state, maybe a notation here, notation for let's say some eta and omega fixed two configurations. This state space here, f, when you put lambda and an age, if we fix these boundary conditions, this is going to be by definition the state space with f, and here we're going to put lambda. The first external field is going to be the external field with that induces the eta boundary condition, and the second one will be the external field that induces the omega boundary condition. Again, for any f local. Every f local. And I think this definition is very intuitive because, for example, what happens is that these states, as we define it here, the configurations are sort of independent. So if you're trying to, so if you consider functions that only depend on the first coordinate, you get the first state. And if you consider local functions that depend only on the second coordinate, you get the second space. So, for example, if you consider this space of, let's say, sigma x of eta y and lambda h, right? This here, as you can check, this is just the state space of, you recuperate the first boundary condition. And you have the same thing for the other coordinates. So if you integrate over the second space, you get just the usual space for this boundary condition, second boundary condition. Okay. For, I don't know, for those more familiar with probability, this is an independent coupling. There's no dependency here, so that's what you're doing. And I think that's all we need regarding definitions. Yes, another very cool thing using these things here is that, I mean, you may be thinking, why are these things useful, right? And using this, you see that why those variables are useful. Because with this definition here, you can see that if you look at the mean of tx, let's say, what's the mean of tx when you put two boundary conditions? Again, this is a state. This tx is linear, so okay, let's make a very small computation here, just to warm things up. Let's say. Yeah, we're gonna do a lot of this. So let's warm things up. If you wanna calculate t of x, right, eta y lambda h. Again, this is the sigma x minus sigma prime x, and eta omega lambda h. Again, this thing is an expectation, so it's a linear functional. You can choose how you want to see it, but it satisfies sigma x h y h omega x minus sigma prime x eta omega y. And these again, as you see, these things they are not dependent on the second coordinate, on the second and on the first, so you just recuperate the mean, the difference of the mean with these two boundary conditions. So this is sigma x, and here you have the different boundary condition, omega lambda. You see, and well, you can, as you can imagine, we're gonna choose this as the plus boundary condition, this as the minus, right? This is the one we're interested in. Yes, right. That's a nice warm up. So let me tell you what are the duplicated variables inequalities. I'm not gonna prove it because I only have 2 hours. By the way, let me just say, maybe not prove all the details, right? I'm gonna leave some things to you because I'm not gonna be back here. But let's get back into topic. Duplicated variables theorem. Again, duplicated variables inequalities. Let me put all the details here. Maybe it's easier for you. So for jxy x and y on the VD non-negative, and we have the external fields h x in ZD, h prime x on ZD. Also, no negative, satisfying we have to satisfy this hx plus 8x prime bigger than 0, and hx minus h prime bigger than 0. To highlight this, so this is important. This is what gives us the restriction on the external field. We have So let's say for all x and y subsets of the box, let me put this there. I'm gonna need a little bit of space for all x and y subsets of the box. Three things hold. First, this thing holds tx age lambda lambda prime s of y lambda lambda prime of h prime. This is bigger than if you consider the product tx s and y. Right. Again, lambda h prime, and moreover, this is positive. This is the first inequality. The second one, meaning that these things are negatively correlated. But when you put t and t or s and s, they are positively correlated, which reads this. So let's say tx ty lambda h prime is bigger than the product. So tx lambda h prime times ty lambda h prime. And you have another one that unfortunately is not going to fit in here. I'm thinking, okay, I'll remember this later. Okay, and you have the third one that, as I said, you just replace t by x. So s of x, s of y, lambda h prime is bigger than the product. S x lambda h prime, s of y lambda h prime. And let me make a remark here, a very important remark. Again, we want to see states with boundary conditions, right? So an important remark is that okay, I don't know if Lucas defined order on the configuration. So let me just do like this. For every configuration, for every configuration here, what happens is that the external field with plus boundary condition at x plus the external field on x with this eta boundary condition, this is larger than 0, and as you can imagine, plus boundary condition say x of eta, here's a minus, right? This is also bigger than 0. You can see that because what happens is that you're summing a term here. Maybe let me do the second one, right? Because I think it's the one that it's the same thing. So I'm just gonna do one of them. Okay, so here's the computation. So h plus x minus hx at. It's just, again, this is hx plus the boundary condition j, x, and y, x, x different than y on the exterior of the box, and you have minus this, minus, again, the other terms, hx, minus, and you repeat the same thing, j, x, and y, but now, make some space here. Now you have the eta configuration, right, at y. So again, x different than y, and y must be outside of the box. So you see, these terms here just cancel out. And for each term here, this term may maybe just be equal to this, but never larger. So again, simple computation. Meaning that you can replace these inequalities by choosing h and h prime as h plus and h of a configuration, which in our case is gonna be just put the plus and minus boundary condition here. Right? You just replace this by plus and minus boundary condition, and you're gonna get the same inequalities. That's the one we're gonna use. Maybe if I have time, I might even write it down. Okay, I think I'll manage it. So let me write the equations we're gonna actually use. Oops. No, yeah, that's right. So let's say corollary, right? Again, in the same hypothesis, right? In the same hypothesis. We have one negative rho x and y on lambda dx plus and minus h on h. Here you have s. Yeah, my handwriting is not great, I admit. So s of y plus and minus lambda h. This is bigger than the product, dx x of y plus minus lambda h. Second one is dx dy plus and minus lambda h. This is bigger than the product, dx dy plus and minus lambda and h. You see why I was reluctant on writing this, right? So x and y plus and minus lambda h. And, this is positive, no negative. X plus and minus lambda h. Okay, so y plus and minus lambda h. And this is what we're actually gonna use. Okay, all good? So let me now state the proposition we will prove. Maybe we don't. I think we have enough space here. So opposition. Proposition again. I'm gonna write everything here. Select J, J, X and Y, X and Y on ZD. I'm just gonna put the external fields here. X, X on ZD, and H prime X, X on ZD. What else is this? No negative. Everything must be non-negative. And we have another assumption we need to make with J, X, and Y strictly for X and Y neighbors. Okay. This thing is new. I'm gonna comment at the end of the proof. I'm gonna comment on this assumption, right? You can replace this by a lot of other things that still hold. I'm gonna comment on that later when it comes to it. In terms of assumption is that, oh, we don't need another external field. Visual. And again, let this then, and then the states, the mean of the state plus, here we have that external field H is equal to the magnetization at in X, which is external field for all X in ZD if and only if the magnetization matches at 1 minus H for some X in ZD. As I promised. Good qualities. Right. And well, I think I'll be able to give, yes, lots of details on the proof. So let's do it. Proof. So okay. So first we fix X and Y on ZD. Okay. And no, take a box. Fix X and Y in ZD. Neighbors with X and Y equals 1. We take that, and we take a box that contains, take lambda that contains Y and X and Y. So you take a large box, any box. Let's first assume something, and then we're gonna prove it. So first, assume assume that we have this following inequality, that t x ty, again plus and minus lambda h, it's bigger than this thing here, tx and y, tx dy plus, here gonna plus also, and here the set is only the two sides and the semi-external force, and also that this is positive. Okay, so let's assume just two things. We're gonna call it just gonna call it star. After we prove this after. So assume this holds. Then you have this trick here. We can write so you can write a difference at x plus and minus plus lambda h minus sigma x minus lambda nh. You can write this, as I told you, as tx, right? Tx of the duplicated variables, lambda and h. And the thing is, this thing here is equal to 1 over 4, and this is a very dirty trick, tx, and here you're gonna put ty squared plus sy squared plus and minus, again lambda and h. Why does this hold? Because this quantity here is constant, is equal to 4. Because if this ty is plus or minus 2, then this thing here is 0, right? When this is positive, it is equal to 4, and this is 0. And when this here is positive, then this here is 0, and is always 4. So this thing is actually a constant. It's just 4. And here can erase also. And now we use the inequalities. So let me just write this again. So this is 1 over 4 tx ty squared by linearity, right? Plus and minus lambda h plus tx s y s small y plus there's a square here, plus and minus, and plus and minus h. Okay, so let's see. By the first inequality, we know that things of this form are always positive, right? Things of this form are always positive. So this is always positive. Yes, this is always positive. I'm just gonna lower bound it by 0. And this thing here, you get, you can split it, right? So this thing here is actually bigger or equal than 1/4. And here you have tx, ty, here is small x plus and minus lambda h. And here you are left with ty plus and minus lambda h. Okay? And again, let me just rewrite that as the difference. So it's clear what we're doing. Tx, ty plus minus lambda h. And here you have the difference of this y plus y minus lambda h. Right. This means that as we are assuming this star equation, this thing here is strictly positive, right? Since this is strictly positive, and our upper bound is the difference on the magnetization, this means that when this is zero, this term here is zero. Okay? So we conclude that the conclusion is this if this is equal lambda h minus lambda h, then the same holds for y plus minus lambda h lambda h. Not exactly lambda h. We are not assuming the local states are coincide, right? We are assuming that the infinite states are coincide. So we just take the limit here as lambda goes to infinity. We take maybe a box. We take the limit here. So if this is zero in the limit, then this would also be zero in the limit. And okay. So let me just erase lambda here. Oh, yeah. And one important thing that maybe I put this inequality here, right? So you may be thinking that it is superfluous, but it's not. This means that this ty here, it is bounded away from zero by a constant that do not depend on lambda. You see, because what might happen is that, yes, this inequality holds, but when we take lambda growing, this thing might go to zero also. But it does not happen because it is bounded away from zero, really. These things do not depend on lambda. Okay. Yeah. That's why this inequality is important. Yes. So we are left to prove this. Before I'm gonna go back to the comment I said I would do. Why this restriction is here? You see why? Because we proved that if this guy coincides, then all its neighbors coincide, right? But if all the neighbors coincide, then all points should coincide because the lattice is connected. So you could replace this thing here by I don't know any you need to basically have the following property. Given two sides in the lattice, they are connected by edges or by vertices with positive interaction. This should also this would also prove what we want. Since I'm gonna use this inequality, I'm gonna leave it here. And we want to prove star now. Okay. I think I can erase this. Okay. So okay, now proof of star. I'm gonna erase that part. So let me write again here. What is that? It's something like this: dx dy plus and minus lambda h is bigger or equal than dx dy. But now you have 2 plus boundary conditions, and you are on a smaller subset, and you have h. This is okay. So this is what we're gonna prove. first, to get a lower bound on this, we're gonna see that it is actually decreasing on the external field. So I'm gonna show maybe. Let me see. I think. Yes, I have. Okay. So we're gonna differentiate this thing with respect to one external field in one side, any side. And I think you made this computation a lot already, right? Differentiating the pressure and so on and so forth. So I'm just gonna write the Hamiltonian down in the right way, and you're gonna see what the differentiation should be. So you can write the Hamiltonian of the duplicated system. Here I'm gonna fix the. I didn't define this, but I think you know what I mean, right? The Hamiltonian with plus and minus boundary condition of that state. So you have sigma and sigma prime, and this is what? This is your summing over x and y on lambda j x y, and here we have two terms, right? So sigma x, sigma y, but we also have sigma prime x and sigma prime, and you have the external field, so h x x, and maybe x is not a good name, right? Because they are fixed, but I hope this is not too confusing. And here you have sigma x, and you have sigma y, sigma prime x, and you have the external field, the boundary condition actually. So it's a minus everywhere, right? Minus, minus. So the boundary condition is for spins different outside of the box. Just j, x, and y. And here you have sigma x minus sigma prime x plus boundary condition and minus boundary condition. And we can rewrite this Hamiltonian using these t and s variables. So this Hamiltonian is also equal to plus and minus sigma prime over y. Okay, j x y here. This term will be a little bit different, right? So let me write that later. The other two terms are easy, right? They're already there. So you sum hx x on the box, and here you have the sum. So it's s of x, and the boundary condition term is just now this middle term here. I'm gonna write it first, so we just reduce it after. This is x, x, s, y plus t, x, t, y. Okay. Let me make this computation. Y, because you just expand everything, and you're gonna see that this works. Tx, ty, sigma y plus sigma y prime plus here I have the difference. So it's just sigma x minus sigma x prime sigma y minus sigma y prime. And this thing, okay, maybe there's a constant there. Let's see. So here I have sigma, the crossed term, sigma x, sigma y, and here I have two crossed terms. Oh, I have this also, sigma prime x, sigma y Yes, I think here we have, I think I have to divide by 2, right? Yes. Now the mixed terms are just sigma prime x, sigma y, and sigma x, sigma y prime. And you're gonna see that this thing here is gonna be the same thing, but we're gonna change signs here. So the other thing is just plus, right? Sigma x, sigma y, the crossed terms. Again, the crossed terms, sigma x, sigma y prime. And here, the crossed terms are gonna have minus. So sigma y, sigma x, sigma y prime. And there you go. Okay. So now we rewritten the Hamiltonian. Not all of this is actually necessary for now, but it's gonna be useful later. So okay. So actually the Hamiltonian has this form, right? And as you may guess, as you did it before, if you don't, if you didn't, I'm gonna say it's an unofficial exercise. You can see that when we differentiate with this with respect for, I don't know, some age z for some site, it's just gonna, we're gonna have this extra term here on the mean. So let me write this down first. So what happens when we differentiate dy and dj lambda h plus and minus. Here with respect to some dhz, where z is a point in the box. As you may imagine, or you may not, but it's the same computation you do for differentiate, I don't know, the magnetization. Yeah, there's sort of standard trick. This is gonna be, oh, ty, no, tx, right? Tx and ty. Oh, yes. So this is gonna be tx, ty. And now you get the term as z plus and minus lambda and h. And you have the minus term here, tx, ty plus and minus h. And here you multiply by the s of z. S of z plus and minus. Okay? Again, I will not make this computation because it's quite tiresome, but you can try for yourselves and this is gonna work. Okay. So what happens in particular, if you look at this thing, we know by inequality 1 that that thing there is negative, right? So this here is smaller than, right? Yes, yes. This thing is bigger, so this is smaller than 0. Meaning that this correlation is decreasing on the external field. And we use this to again do another standard trick. So okay, this is decreasing. So if we consider take, I don't know, some lambda positive in the external field. The external field. The name of the external field is going to be h plus lambda x and y. Not a good name, but a useful one. How this external field is defined? At a site z, you just copy the external field, but you add this parameter whenever z is not is not x or y. X and y. Z on ZD on lambda. ZD. Okay. So you are adding a constant external field in all sides except on x and y. And you can clearly see that as this lambda is positive, this external field is always larger in any site. This quantity is always larger than just the original external field. This thing is decreasing. So we can lower bound this by let's say therefore this here, the original thing we wanted to bound, plus and minus lambda h is actually smaller than dx dy plus and minus lambda, and now we have this external field lambda x y. Okay, so we have this upper bound, and the idea now is to take the limit when this lambda goes to infinity. That's the goal. Okay, let me leave this here. Maybe we can erase this. So now our goal is to compute this limit. Again, to do so is a sort of standard trick. So how do you do it? We just maybe just write the state in the right way. So this is plus and this is minus, this is lambda, and here we have to change the external field. This is what? So we sum overall configurations, right? Omega lambda, and you have dx and dy here, and you have exponential of maybe I'm gonna write this in the proper way. So here we have the Hamiltonian with the original external field. Okay, but we have this the original external field, but now we have an extra term. This extra term is this, so exponential of beta, and we sum over x. X is bad, right? On z, on lambda, and here we have lambda times the configuration. It's sigma. Let me use the Hamiltonian on that form. So here we have t z. Right? We call that our Hamiltonian is of this form here. So the terms multiplying the external field are s. Actually, s of z. Oh yes, and this Hamiltonian is the duplicated one, right? Here, so plus and minus sigma prime. Okay, so the original Hamiltonian and the extra term. And now we divide by the partition function is just the same. I'm gonna write here. So you see exactly what is happening. So lambda, and now we just have original Hamiltonian plus and minus sigma prime and exponential of beta sum lambda as z. Z on the box. So the trick is to rewrite this thing, maybe not a trick, But again, let's rewrite this thing in this form. So again, sigma prime here. We have the same tx and ty. And the Hamiltonian is the same. So beta, the original Hamiltonian, plus and minus sigma prime. But this term, depending on the external field, you just write it as exponential of beta, and you take some z on the lattice of lambda times 2 minus s of z. Of course, you cannot simply do that. You have to divide by the partition function. Let's hope it fits here. Sigma prime omega lambda. Yeah, you won't. So I'm gonna rewrite it down there. But the trick is to multiply both sides of the equation. You multiply this by e beta minus beta 2 sum of the sum on z. Let me put it like this. So you multiply and divide by the same thing. Sum of 2 z on h. Okay. I'm gonna leave this Hamiltonian here because we're gonna need it afterwards. So when you do that small trick, you get that the difference of the state of tx and ty on plus minus lambda h plus lambda x and y. This is sum tx, ty. Here you have the configurations. Exponential minus beta Hamiltonian, lambda h plus minus sigma prime. And now I have what appears here, exponential of minus beta lambda sum of g on the lattice 2 minus s z. And the partition function is the same thing happens. Sigma prime of omega lambda and exponential of minus beta h plus and minus lambda h sigma prime. And the same term, exponential minus beta lambda sum of z lambda 2 minus s z. Okay. Oh yes. It's not on lambda, right? Because we are only adding this lambda term on the vertices that are not x and y. X and y. That then also we are just adding this thing on the vertices that are not either x or y. So, which is neither x or y. And here the same thing. So either x or y and either x or y. And now what we need to see is that this thing here will be 0 whenever sz is not, if sz is not 2 for some z, then this thing is going to be negative, and it's going to go to 0, right? So this term that appears there, this minus beta lambda sum of 2 minus sz z lambda minus x and y. This converges to wait. Yes, this here is for when sz is 2. So this thing here, when sz is 2 for all z's, this thing is going to be constant, right? Because this is going to be 0, whatever. If for some site, this thing here is not 2, sz is not 2, then all this term here is going to go to 0. Why? Because you can just write this as the product, right? So this is just the product of z on lambda minus x and y of the exponential term, exponential of minus beta lambda 2 minus sz. So if this thing here is not 0 for any site, then all this product is going to go converge to 0, because one term is going to converge to 0, and the other are bounded, and so on and so forth. So this thing here, it does not converge to 0 when lambda goes to infinity, if and only if z is equal to 2 for all z in the box. They are not x and y, right? So for all configurations that do not satisfy this, all these terms, both here on the numerator and on the denominator, it's going to go to 0. And now, well, what does this mean? Hence, when we take the limit, lambda going to plus infinity of this thing here, tx. Yes, I have to watch out for the x and the y. Tx plus and minus lambda h. When I take the limit, I have this x and y. This limit here is exactly tx and ty plus and plus x and y, and here you have the original external field. And to see this, you actually just look at the sums here, and whenever the configuration is not something here, whenever the two configurations are not in here, if sigma or sigma prime are not in here, in the omega plus x and y, they are not a configuration of this form. So the term in the sum here will vanish, because again this term is going to go to 0. This is going to go to 0. So in the end, you're going to kill all the configurations that are not of this form, and all the configurations going to left are the configurations here. And for the configurations here, this term is 0, is 1, right? So this is 1, and you are left with the original Hamiltonian and the original system. So that's why this limit exists. And we are almost there. Yeah, I'm gonna have a few. So okay, so we have this limit, and remember that the lower bound, which is external field, holds for any lambda. So in conclusion, the correlation we are interested in, plus and minus lambda h, is bounded below by this thing here. Right. Dx, dy, plus and minus. Here we are only on x and y and h. Right? Yeah, we are almost there. We only need to prove that this quantity here is strictly positive. And this again is very easy to see once we write the Hamiltonian of this form, on this form. Okay. So we are not going to need this anymore. Okay. So let me write this here explicitly. So tx and ty plus and minus, but only on x and y. This is what? H. This is what? I need to sum only. First of all, I need to sum only when tx and ty, they are either 2 or minus 2, right? Because otherwise they are 0, and as we have a tx ty term here, this is just going to be 0, so it doesn't matter. Also, let's just write everything. So here, exponential of beta, and here you have the Hamiltonian. So we only have two spins, and the nearest neighbor interaction is x and y. And now it appears x, y, x, s, x, x, y, plus dx, dy. I'm going to erase everything, so we do this only. Okay, so this is the interaction between two spins, and now we have external fields, right? So the external fields is, I have the external field on x, which is okay. So here I have s x plus h y s y, and I have the boundary condition term. So the boundary condition term is plus sum of the neighbors of y of x js jx y. Let me here. Y speaks it right. Not a good letter again. So z. Let's go for z. So I have z on lambda. We have j x z and z and t x plus some, again, z on the complementary. We have y, j, y, z, t, t, z, so t, y. Okay, now I just noticed that I made a slight error in my preparation. Maybe I can fix this. Otherwise, I'm gonna pretend I'm gonna add another restriction on the term. Yes, I think I have to do it. It's basically because this minus is outside of lambda, and the lambda, yes, okay, maybe, yeah, maybe you have a point there that I should take lambda large enough because, I don't know, maybe x is right beside lambda, right? Maybe x is here, and your lambda finishes here. So this might happen. Yes, this is actually a great observation. So let's assume, because lambda is arbitrary, right? So we can assuming that maybe the simplest way of doing this is, let's say, the distance of x and y to the complementary is large. No, too large. Okay, because when you do that, then these bad cases do not happen, and the state sites are really inside the lambda. And when you force this external field actually forces everything to flip. But you're right. So now this works. Well noted. Yeah, okay, let's go back to that. And okay, so first of all, we notice, as I said before, when these things happen, as both are positive, all the s's are 0, right? So there is no more s here. So let's just, there's a partition function. Just so I don't write it down every time, I'm gonna put this here. So here's times the partition function, right? Lambda no, x and y, h plus and minus plus and plus is equal to 10. So let's first erase all s's. Gx, gy, 2 and minus 2, and gx and gy, and exponential beta jx, y. Here I have gx, gy, gx, gy, and then I have this is 0, and I'm left with that. Oh, okay. You see, that's why we cannot rush things. I actually lied to you here, right? Because this Hamiltonian is with minus boundary condition. But now we have plus boundary condition on both systems, right? So let's, okay, you can see, let me make the necessary changes, and you say if that's okay. This is Tx, right? Because this is the difference of the system. This here is sigma x minus sigma x prime, Why? This minus is because we had minus boundary condition, but now I have plus. So this is plus, and this is S. Okay. Right? Yes. Now I'm saved again, and I don't have to worry about. And the same thing goes here, right? So this is actually S of X, S of Y, and again I'm saved. So all terms here just finish, and I'm just left with this. And now it's basically over because when you take ty matching signs, if you take ty both equal to 2 or plus 2, you're gonna have 4 here, right? And 4 here. So for the positive terms, as we can have both 2 or both minus 2, then this is 2 times, and here is 4, gx into y, and exponential beta j x y times 4. And when they change signs, again, I have just 2 cases, so it's minus 2, because now they change signs, times 4, times the and beta j x y and 4. And you see in here, you see why we need again why we needed that assumption, because this is there's a minus here, right? Because they changed the sign, so this is minus 4. And now see why this is always positive, because the nearest neighbor interaction is not 0. You see, again we're using that. But again, if you had a path connecting two sides with positive interaction, you could do the same argument. And that's basically it. We proved that this is actually positive. We had proved the second equation, and that's all we needed. Okay, this is the proof. I have nothing else prepared, and that's it. Do you have any questions? Okay. Yes, that's a good. So, yes. Let's. Yes, enough of technicality. Let's just apply this to our real model. Yeah, why we're doing this? I will just erase this. So, as you remember, maybe you don't. You've seen with Lucas the Ising model with decaying field. Which is what is this decaying field? The decaying field is something like this. So decaying field. Decaying field. You take this the external field as one or maybe H star. Okay, H star is just a constant. H star is a positive constant, and you divide this by maybe x is fine here. Let's go back to x, and you divide by the distance of x to 0 to some delta. Delta is again a positive term. Okay. And remember, this is the decaying field, right? It's a field that it decreases as it goes away from the origin, and you see when you put this field, we do not have actually a translation invariant system anymore. So in the statement of in the previous result we have before this stronger version, you had to, if you want to prove uniqueness, you had to prove that the magnetization in every site must match. So you need to take any site and prove that the magnetization matches, which might not be optimize it here because you have a lot of dependency on the energy on the site you're fixing. But what our or improved version shows is that it is enough to show that the magnetization at 0 matches. So what we can actually take from these results is, I don't know, a proposition. Consider the another important thing, you see that the interaction is very general. As long as it's ferromagnetic, you're okay. So you can consider nearest neighbor Ising model, or you can consider any type of Ising model. I'm just gonna put the nearest neighbor here. I mean, consider the nearest neighbor Ising model with the external field. Let me give a name for this here. Let's say the decay. Okay, with external field H deck. Then there is uniqueness. If and only if the magnetization at 0 H deck, right, is equal to the magnetization at 0 with H deck. And there are actually another model that we actually need to use this to prove uniqueness. It's called the semi-infinite model. So I don't think I have it. Yeah, I think you need translation variance. Yes. 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 Yeah. Any interaction. Ferromagnetic. Yeah, it's inside. Yeah. Let me just say that these duplicated variables inequalities, they are actually very useful. You can prove a lot of other things. We can, for example, I think even the papers on the extremality of the plus and minus, they use this in some sense, but I don't know exactly how. No, no, there is no property of the graph. Yes, thank you.